Okay, we ready to start? Okay, we're recording. Everything's good. And I saw that at least the mic looked like it was working. So, all right, welcome everybody. So, I think this is where we left off last time. So, a couple of slides here on bioavailability. So, organic acids improve bioavailability of elements in our diet, minerals. So, they can do this in a couple of different ways. Number one is just simply they're acids, and so they're going to increase the solubility of these elements. So there's one thing, that kind of the easy one. And the second one is just that these organic acids you can see can create either complexes or chelates with these elements. So what you'll want to start looking for is it going to form a complex or a chelate? So acetic acid just has one ionizable hydrogen on it, one proton that can come off. So that one obviously can form just a complex. Remember, a chelate has to form an interaction in at least two places. These others, though, can all form chelates. And it's a little bit maybe difficult to see it, but first of all, citric acid has a lot of ionizable protons. It has 3 of them here. And so all 3 of those can orient themselves in a way to interact with these elements. So citric acid can bind in more than one place because it has all these ionizable groups. Lactic acid here only has one carboxylic acid group, so one ionizable proton. Let me point to it here. So, this proton is the acidic proton. But what happens if we have an element sitting right here? We can form an interaction with this negative charge here. And this oxygen is also partially negatively charged. So if we have, say, an iron or a calcium sitting right here, see if I can draw this. It's going to be super awful. But let's say we have, oh, how come it's not showing up? Oh, there it is. So let's say we have an element that looks like that. So it can interact here, and it can interact with this oxygen here, like this. And so now we've interacted in 2 places, and we have formed a 5-membered ring, which is really stable for these ligands, remember? So that's good. Same thing with ascorbic acid. Let's say we have, see if I can maybe draw it better here. This is going to be iron. So we can interact right here with this oxygen, and we can interact right here with this oxygen and form a 5-membered ring. So, number one, they're acids, so they're going to lower the pH and make these elements more soluble. And for many of these elements, solubility is basically the most important factor about whether or not it's going to be absorbed. And then second would be the possibility of forming a chelate and maybe even forming a complex. In the case of acetic acid would be helpful, but certainly forming a chelate with these other acids would be helpful because these would be soluble chelates and they would be readily absorbed. This large compound here is phytic acid. And phytic acid is it's a ring structure with a lot of hydroxyl groups on it. It looks like a sugar, but it's not a sugar. That compound in the middle happens to be called a inositol, but that's not that important. The important thing is that we have all those, these are mixed esters, so phosphate esters. Okay, and there's 6 of them around this ring. And so there's a lot of phosphates, which means there's a lot of negative charges here, highly negatively charged. So you can see all these opportunities to chelate metals here along this ring. And this, when this compound interacts and forms these chelates, it becomes insoluble. And so bioavailability goes way down. This is a naturally occurring compound in many plants and seeds that we eat, grains, beans. So chelation of these metals onto phytic acid will lower the bioavailability. Unfortunately, there is not a way to look at a structure and to know if that chelate is going to be soluble or not soluble. So the chelates that we formed here are soluble and increase bioavailability. The chelate that we form here is insoluble and decreases bioavailability. So you kind of have to remember which ones are going to be soluble, which ones aren't. But really in this class, there's just 2 that aren't, and that would be phytic acid and oxalic acid. So both of those 2 form insoluble chelates and decrease bioavailability. There's an enzyme called phytase that occurs in the same places where phytic acid occurs. So in grains and beans where phytic acid is really high, they also have phytase. And so if our processing method for those grains or those beans allows for that enzyme to become active, then we're not going to have this problem and those elements are still going to be available for us. So for instance, if our procedure involves making bread, so we're going to make whole grain bread, and in making bread, we have to let it rise for a long time. Those conditions are really good for enzymes to become active because now there's a lot of water around and it's going to be warm, not too warm, but warm for these enzymes to work really well. And so if we have that long fermentation time for making bread, this phytic acid is going to be degraded and those elements are going to be released. If we took that wheat and instead just boiled it right away, that wouldn't happen. But if we had that long fermentation time. Likewise in beans, the first step in making beans is usually to soak them for a long time, to hydrate them before you cook them. So during that time, phytase can start to work. The beans are still whole at that case, so the enzyme isn't great at being active because of the enzyme and the compound there are generally in different cells or different compartments in the bean, but it can help to reduce that. So one way that processing can reduce this phytic acid and free those elements is by creating conditions that enzyme can work. Okay, these are polyphenolic compounds. And usually people would call these catechins. You see the compound in the middle on the top there. This is called catechin. This is another example of a CH in the name where it just sounds like a K or a C. So it's not catechin, it's catechin. But anyway, that's a catechin, and then the rest of them would be in the group of catechins. They're just substituted catechins. And so these are polyphenolic compounds in a lot of different plants, but most concentrated in tea, green tea or black tea. And these compounds form chelates with metals in the same way that I showed for ascorbic acid. So we could have a metal right here, and we can form a chelate like this with these oxygens. So a 5-membered ring chelating with the partial negative charge on the hydroxyl groups, on adjacent hydroxyl groups. And you see those are quite prevalent in these compounds, right? There's some pictures on here where you can see that that could occur at many places in that compound. These complexes here are insoluble, so they reduce bioavailability. Actually, so there's a third one that I didn't mention before. So a lot of these naturally occurring compounds, they form chelates that reduce bioavailability. So during processing, we can lose these micronutrients. Some cases we can increase them, and we'll talk about that too. But we can lose them. And in contrast to the vitamins, in vitamins, a lot of the loss was because of heating, like degradation. You remember, we talked about the methylene groups between those rings on folate or on thiamine that are very unstable. And we talked about degradation of vitamin C because of heat. That doesn't happen with elements. They can't degrade. They're just elements. So they're like the smallest thing that they can be. So how do losses occur? Well, they occur as a result of the pictures over there. So number one could be physical separation. Like when we peel that cucumber. So if it happens that these elements are concentrated in the skin, if we remove the skin, then we've lost them. So physical separation. And then the second one that we might lose is down there, just leaching. So if these are water soluble in some cases, and so they can leach into that blanching water or cooking water. And then if we don't drink or eat the water in a soup or something, then we don't get those nutrients. Come on, I'd really like to be able to advance slides without exiting out. So here's another example of physical separation that's maybe not as obvious as peeling something. So this is making cheese. So as you know, when we make cheese, we precipitate out the casein proteins, and that's what cheese is. And sometimes we might not think about that as a physical separation, but we're separating out those proteins, and then we're throwing away the whey. So anything that was left in the way, we lose. These are 3 kinds of cheese. And we have there the pH when we remove the whey. So cottage cheese is very acidic. And so when we remove that whey, it's acidic whey. And so there's going to be a lot of elements in that whey, particularly calcium. And so cottage cheese is super low as far as dairy products go in calcium, because we lose it all in the whey. In contrast, these other 2 cheeses, cheddar and Emmental, are the pH is much higher when we remove that whey, because we do it with an enzyme instead of with acid. And so pH is close to neutral, and so the cheese takes with it a lot of the calcium. So those are good sources of calcium. So the processing there has a big effect on whether or not that cheese is going to have calcium, and it would be, physical separation of this milk that's causing that change. Same thing with the phosphate, but we usually don't worry so much about the phosphates. This is physical separation during milling. I think this one is maybe not as interesting and probably kind of obvious. When we take a grain and we mill it into white flour, we take off the bran coat, which has a concentration of a lot of the elements and vitamins as well. But we add a lot of those vitamins back to white flour. But we don't add, except for iron, we don't add the elements back. And so we lose a lot of those. Especially we lose magnesium. So, and that is one that people generally aren't getting enough magnesium. That's one that isn't added back and is lost. Same with zinc too. Okay, processing, I mentioned, can actually increase these micronutrients. And, we don't actually make them in the process of making the food, but we might make them more available for absorption. Okay, so this is an example here. Actually, this is from one of my students, but she took some pinto beans and extruded them into these pinto bean snacks. And then she measured tannins. So tannins are polyphenolic compounds. They're similar to those ones that we saw here, but larger. And in the beans, they were very high, but after extrusion, they were very low. That extrusion process sort of degraded them or oxidized them in some way. And so then she measured how much was bioaccessible. And you can see, if you just are measuring the raw flour, that would be on the left there. It's much lower than on the right, where we have the extruded product for both iron and magnesium. So during processing, because of the degradation of those tannins, they're not going to form those insoluble chelates, and so these elements are more bioaccessible. Okay, so let's talk about some specific elements. And we're definitely not going to talk about all of them, but we're going to talk about a couple of them. So first we'll talk about calcium. And just so you know, I think for the interest of time, I'm going to skip about 3 slides here. So if I skip a slide, you notice, you can just skip over it. Okay, so calcium. there are a couple reasons that we would put calcium in a product that have nothing to do with the fact that it's a nutrient for us. So similar to what we talked about with vitamin C, sometimes we put vitamin C in a product just because it helps the quality of that product, not because we want to make it a good source of vitamin C. Same thing here. Sometimes we put calcium salts in things just because we want the calcium to do something, not because we want it to be a source of calcium. So I know that this is kind of small. These are just diced tomatoes. The ingredient statement is small. But what you'll see is on that ingredient statement, you have, let's see if I can find it. Here it is. It's on 2 lines, calcium chloride. Okay, calcium chloride is added to these tomatoes. It's almost the last ingredient, so that we know there's not very much of it in there. And then if we look at how much calcium there is, it's not that much. So why is that calcium chloride in there? It's not because we want tomatoes to be a good source of calcium. Well, so calcium chloride could definitely reduce the water activity. But we would have to have a couple of molar concentration. So it would have to be very concentrated. Here, it's very, very dilute. So it's not actually affecting the water activity very much. What it's there for is to retain the texture of those tomatoes. So during this long heating process, those tomatoes are going to completely disintegrate into mush, which may be desirable if you're making a sauce, but if you want to have tomatoes that the consumer can actually still see when they open that can, then you better put something in there to preserve the texture. So in tomatoes and in all fruits and vegetables, we have some cell wall polysaccharides called pectin. The pectin helps to hold the cell wall together. So cellulose is, you can think about cellulose as forming the 2x4s that build the cell wall, and pectin is the glue that sticks all those 2x4s together. And as we heat the pectin, pectin has a lot of uronic acid groups in it, which are sugar acids that have a carboxylic acid group on them. So I can draw pectin. Pectin is a polysaccharide chain, and it has some acid groups sticking off of it. So it doesn't just have one, it has several. And some of those acid groups are methylated. Okay, so they might have a methyl ester attached to that acid group. Okay, so what happens if I have another pectin molecule right here that has a negative charge on it like this? So we have 2 negative charges. Are those going to attract each other or repel each other? Repel. So what do you think that's going to do to the texture of those tomatoes? Make it squishy. Exactly. If pectin is the glue that holds everything together and that glue is repelling itself, then it's going to become more squishy. So we can add calcium here in the middle that has a 2+ charge. And now that's going to form an interaction with these two. And now, do they repel each other? No, they are actually attracted to each other now. So that's going to strengthen that texture. And I showed you this here, the methyl ester, because this is how it occurs mostly in the tomato. But as we cook it, some of those methyl esters come off, and we get more negative charge. That's why we get so much more softening. And so if we have that divalent cation in there, could be anything, but calcium is usually used. If we have that divalent cation there, then those pectin molecules, instead of starting to repel each other more and more, they become attracted to each other, and we retain the texture of those tomatoes. And this isn't just exclusive for tomatoes. If you go and you look at your canned vegetables, almost all of them have a little bit of calcium chloride added to them to preserve that texture. So there's one reason why we put calcium in. Here's another reason. This is tofu. So tofu is made from soy milk, which has a lot of soy protein in it. And here's the ingredients down here. We have calcium sulfate added, and we have calcium chloride added. This has 10% calcium. So it's getting up there. We have a lot more here than in the tomatoes. And in some ways, the calcium salts here are to make it a source of calcium, but they're performing a very important function. So if we have a protein like this and another soy protein like this, these soy proteins are negatively charged. They have lots of negative charges on them, both of them. So they have overall, there's some positive charge, but a net negative charge on these soy proteins. So just like we saw with the pectin, if we add a divalent cation, calcium, then those negative charges can be neutralized by the calcium, and instead of those proteins repelling each other, they attract each other. And so in the soy milk, those proteins are all repelling each other, and so they're in solution. But when we add the calcium, they attract each other and they precipitate out of solution. And that's what tofu is, those proteins that have precipitated out. So, and again, we could add calcium or we could add another divalent cation and it would do the same thing. And in fact, the traditional salt for making tofu would be magnesium chloride. But calcium chloride and calcium sulfate are commonly used now because then it makes it a better source of calcium. But we can use these divalent cations to bring these proteins together, precipitate them out of the soy milk, and make tofu. Okay, phosphates. Phosphates are ubiquitous in our food. So they are used for a lot of functions, and you're going to see a dizzying array of functions in the next two slides after this, but they're used almost everywhere. And they're not used as a source of phosphate in our diet. We get plenty of phosphates. They're used as processing aids. So again, these nutrition or these ingredient statements are small, but we have some ham here. We have some sodium phosphates here. Let me actually use a highlighter here. So we have some sodium phosphates. We have over here, we have some a sodium phosphate again. We also have calcium phosphate. Over here on this cake, we have some different phosphates. Here's calcium phosphate, and then sodium aluminum phosphate. And down here, this would be like a cola beverage, Coke or Pepsi. We have phosphoric acid. And then here, this instant pudding, we have a combination of tetrasodium pyrophosphate and disodium phosphate. So, you know, a lot, I mean, you see a wide range of foods here. Meat, cheese, cake, you know, baked goods, pudding, and beverages. All of them have these phosphates added to them. And so I guess just specifically on these, you know, the ham, those phosphates are really there to bind water. So that ham has a ton of water. Here it says with natural juices. Keep those juices in, those phosphates are added. In the processed cheese, phosphates are added for two reasons. To keep the proteins from being gritty, I guess, keep them smooth, keep the cheese smooth, and then they're emulsifiers. So they're going to enable that cheese to melt and be nice and clean as it melts instead of having oil come out and float to the top, like often happens with unprocessed cheeses. In the cake here, these calcium phosphate and sodium aluminum phosphate, these are components of baking powder. So they're leavening agents. Give the cake some leavening. Phosphoric acid in the cola, that's really just there to acidify that cola so that it's more shelf stable. And they use phosphoric acid here both to chelate any metals that are there so that we don't get oxidation of the flavors, and then also to this phosphoric acid does not impart like a sour taste. We don't want that sour taste in these beverages. In like a 7-Up or a Mountain Dew or, I don't know, Sierra Mist or something, we usually would have citric acid there, which is also chelating things, but also we want it there for its sour taste. And then here we have chocolate pudding. The combination here of the disodium phosphate and the tetrasodium pyrophosphate, it says here what they're for. They're for thickening. So these phosphates do two things. They are dispersing agents, which means that they're going to allow the ingredients to disperse and hydrate more quickly. Specifically, the modified cornstarch here. So that modified cornstarch normally would take a long time to thicken. So we would have to let it sit for half an hour, maybe an hour before that pudding was set. But with the phosphates there, it hydrates much more rapidly, and it sets in 5 minutes, I think it says. So much faster. And then the combination of these two phosphates also helps to gel the proteins in the milk. So in a similar way that we saw the soy proteins precipitate out with calcium, with phosphates, milk proteins are going to associate together. They don't precipitate out this time, they form a gel with a negatively charged compound. So if you look at the box for these instant puddings, you will see that it will say, you know, not recommended to use soy milk or any other kind of plant milk. You're supposed to use cow milk because those phosphates will gel casein proteins. They don't gel soy proteins. So you make this with soy milk, it will thicken a little bit from the cornstarch, but it's not going to thicken as much as it will with cow's milk. So here are the different phosphates. So it's important to understand what a orthophosphate, what a polyphosphate, what a pyrophosphate, and the metaphosphate are. So the monophosphate there is usually, that would be just a component of a salt like sodium phosphate or potassium phosphate, disodium phosphate. These are all the monophosphate. And they're often just there. That would be like the leavening agents, a component of the dispersing agents, and so on. We can have a diphosphate, and so that would be just two phosphates hooked together. Or we can have a polyphosphate, where we have more than two phosphates hooked together in a polymer. And these diphosphates and polyphosphates especially are almost always there to bind water. So they're strong, good at binding water. And then metaphosphate just means that those phosphates are linked together in a ring. Okay, and then here are just a list of all these phosphates that are added to foods, what function they perform, and some examples of foods that they perform that function in. But you see that phosphates have so many functional properties. I think it's a little bit cool to point out that phosphates are anticoagulants and coagulants. They are adsorbents, so they'll help to get stuff to stick together. They're also dispersing agents, so instead of being sticky, now they allow things to disperse and not stick together. So they are leavening agents. So yeah, lots of different things here. Sequestrant, so they can bind elements. They can also take proteins out of juices and stuff like that and clarify them. But they can also allow those proteins to gel, stay in solution. So a lot of, like, you know, contrasting functional properties. Okay, iron. So first of all, you should definitely know what ferrous and ferric are. So you'll want to know that ferrous is the reduced form and ferric is the oxidized form. Ferrous has a 2+ charge, ferric has a 3+ charge. The 2+ charge is the one that we would like to have around because that's the one that we can absorb. The 3+ is poorly absorbed. And this reaction along the bottom there, that shows why it's poorly absorbed. So when we mix iron in its 3+ oxidation state with water, over time it hydrates to ferric hydroxide, and ferric hydroxide is not soluble, so it is not absorbed. Iron is always chelated. Either we add a chelating agent or it's chelated in the material that it comes in. This is heme. So this is how iron occurs in, muscle and blood, and also in a lot of enzymes, this heme component. And so it's coordinated there, or forms a chelate there with those nitrogen atoms in that. This is called a porphyrin ring. I see that I can't write that on the screen, so you don't have to worry about remembering that. But this is a porphyrin ring, and coordinated there with the nitrogen. And then usually these kinds of chelates are coordinated in 6 places. So you see 4 there. There's a 5th one that is attached to the protein. So the myoglobin or the hemoglobin subunit, or the enzyme that it's a component of. And then a 6th one where it binds to oxygen, hopefully oxygen, if you're breathing right. And then it can bind with some other things that would be less desirable. A lot of times you'll notice in ingredient statements, they'll add iron. So like in flour, we add iron. And it's usually added as an elemental iron powder. So not 2+, not 3+, not even a salt, ferrous sulfate or something, not even a salt. But it's actually elemental iron. So let's see my cursor here. So elemental iron like this. And I wanted to point out this especially. So this is called reduced iron. It's reduced iron because it's small particle size. The particle size is reduced. Not because it's ferrous iron, the reduced form of the oxidation state. So when we look at that term reduced iron, it just means that that iron powder is a small particle size, not that it's in the 2+ oxidation state. These iron powders must be ionized for us to absorb them. And so these iron powders rely on the acid in the stomach to convert elemental iron to ferrous iron so we can absorb it. That's not super efficient. We do get some, but a lot of it is not absorbed. Okay, iron, we've mentioned a couple of times, is a pro-oxidant. So you'll see this terminology here a lot. This would be a lipid hydroperoxide. And if we have free iron floating around, then this iron can catalyze the breakdown of that peroxide to some pretty nasty compounds. We can also do that with ferric iron. Ferric iron can also catalyze lipid oxidation. So both of them can. But when iron is in the reduced condition, obviously that would be much more of a pro-oxidant because this is an oxidation reaction. So if this is already reduced, it can oxidize stuff really well. And so the reaction rate up here is about 10 times faster than this reaction rate. So iron 2+ is good for us because that's what we can absorb, but it's really bad to have around with lipids. So we must chelate it, and if we've got it around, we hope that it's 3+ actually, otherwise it's going to oxidize all of our lipids. Okay, we got 5 minutes left, hopefully. So we'll talk about heavy metals real quick. We have these 4 heavy metals that are pretty toxic to us. So we don't want these around. Lead used to be a big problem in like dyes and inks and stuff, and so it did come in from our food, just from the packaging, but not so much a problem anymore. So we can not worry about lead from a food perspective, but the other 3 we still need to worry about. Mercury, it can come as an organic salt or an inorganic, organic compound or inorganic salt. The organic form is way more toxic. In especially fish, they accumulate from the sea a lot of methyl mercury, which is an organic form of mercury. And that is super highly toxic. And so you see here how much methyl mercury there is in some seafood. So mostly you just want to remember methyl mercury or organic mercury is the toxic form of mercury, and that we have to worry about it in seafood mostly. A lot, especially shark and stuff related to shark, and then tuna also is pretty high. Salmon, salmon's a fatty fish that you would expect to see it, but it's actually not really there. So, but a lot of seafood we have to worry about organic forms of mercury. Cadmium comes in lots of different forms. I've written them there. All of them inorganic salts or ions. And they're all toxic. So we don't differentiate between inorganic or unorganic like we do for mercury. With cadmium, everything's just bad. This is where we get cadmium. We get about 1/3 of our cadmium from grain products, breads, cereals, crackers, things with flour in them. And then we get another 1/3 from all the other healthy foods that we eat, fruits and vegetables, beans, things like that. So we cover, sort of healthy foods give us most of our cadmium. About 2/3 of it. So there are some regulations, not actually here in the US, but across the world. We have regulations, especially for grain products, since that's the major source. In Europe, less than 200 parts per million, or less than 0.2 parts per million, and in China, less than 1, or 0.1. Cadmium is usually not that big of a problem. Grain products are a really high source of cadmium in our diet because we eat so much of them. But they don't actually usually have a lot of cadmium in them. So there are some places, though, where the soil where those crops are grown is contaminated with cadmium. And so if there have been like industrial activity and there's been some soot contaminating the soil or some waste products contaminating the soil with cadmium, then those plants can actually be very high. It happens that some areas in Nebraska are high in cadmium. So this is data from Nebraska in 2012 and 2013. And you see in 2012, especially, the mean cadmium concentration for the wheat is above 0.2 milligrams per kilogram. So that wheat would not be able to be sold internationally because it wouldn't meet those regulations. Could still be sold here because there's no regulation here. But you see, in comparison to Oklahoma, which does not have contaminated soil, it's 10 times lower in Oklahoma. So kind of a problem. And then last, arsenic. So arsenic, what you want to know about arsenic is it's the opposite of mercury. So with mercury, we worry about the organic form. With arsenic, we worry about the inorganic form. And there's lots of different oxidation states. The most toxic one is this +3 oxidation state, the trivalent inorganic species, this one over here. That's the most toxic one. Rice is what we worry about for arsenic. Rice is what we get basically all of our arsenic from. And the reason that rice accumulates arsenic is the way that it's grown. So usually rice is grown a little bit, and then the field is flooded to control weeds. And in that condition, the conditions become anaerobic. And so any arsenic that's there is going to be reduced because it's anaerobic, and the reduced form is that 3+ oxidation state. So it's going to be in the toxic form. And then arsenic, the roots of rice take up arsenic really well. They kind of, they think it's phosphate, but it's actually arsenic, and they take it up very efficiently. So definitely have to worry about arsenic levels in rice. Okay, I think that's the end of our talk today. So thanks for your attention, everyone. We'll have a review if you have any questions, review on Friday. So thanks.